Hello, my name is Nico Geraldo, and this is Lab 5, Faraday's Law. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of an aluminum foil, model the magnet-tube interaction computationally, and compare my computational predictions with the observed data. The principles I will be using are Lenz's law, Faraday's law, Newton's second law, and the magnetic force on a wire. The results of this lab were that the predicted fall time of 1.129 seconds was very close to the actual fall time of 1.15 seconds. For the experiment details, the initial conditions were that the bar magnet was dropped through the tube from rest with the north pole facing down. The system is the bar magnet and the aluminum tube, and everything else are part of the surroundings. The assumptions I made were only forces are gravity and the force from the loop, and the air resistance is negligible. The details of this experiment, procedures were first I had to mark the north pole on the magnet, so then I knew which end to drop it first. The second part was to measure the mass of the magnet, width of the tube, the inner radius of the tube, and the length of the tube. The third step was to drop the magnet 5 times for my trials through the aluminum tube and record it. Fourth step was to determine the time it took for the magnet to fall through the tube, and the fifth step was to run the Python code with the initial values and measurements to compare with the tested results. So my data and results, the tube length was 0.4 meters. The foil width was 0.005 meters. The inner radius was 0.0125 meters. The mass of the magnet was 0.044 kilograms. The average falling time from the 5 trials was 1.15 seconds, and the magnetic dipole is 5.365 ammeters or amps meter squared. This is my code. At the top, I have the picture or a screenshot of the magnet falling through the tube. On the right, I have the graph that the code produced, the velocity time graph. So for the pieces of code, I have me setting the values for the length, width, inner radius, the combined radius, the mass, other things like that, and then me making the dipole, magnetic dipole function, which was also from lab 3. And then after that is the function to calculate the delta flux over delta T. There's more code for making the force of gravity, and then also dflux dt using the function defined earlier, and then doing the ring current as well. And then below that is the magnetic field at the ring, B hat, just other stuff. And then towards the bottom is finding F net by combining the force of gravity with the magnetic force, and then setting the bar velocity and bar position. So for error, sources of error could have come from incorrect magnetic moment, the magnet making contact with the tube during the fall, incorrectly timing the fall for just human error, and also air resistance could have played a part along with inaccurate measurements of the dimensions. For the what if questions, what if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of the falling magnet change? The current would be extremely large since the resistance would go basically to 0. And the magnetic force from the tube would increase a lot. So the magnet would fall much slower. And then kind of opposite of that with the next question, what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes would reduce the number of rings in the tube because the holes would make the rings discontinuous. So this would reduce the current and make the magnet fall much faster.